last week.
Yeah.
Let's say the week.
All right. So today we're gonna. It's gonna be our last discussion, I think. Right? Yeah, I don't think we have anything next week. I mean,
Yeah,
there's
Monday's
no point.
last
The
day.
exam's on Monday.
Yeah.
I mean, so we can have discussion, but I mean, I don't know. But so. Yeah, I mean, we're gonna discuss. We're gonna do the exam review. So the discussion worksheet has like one problem on it. So I don't think that's enough to review for the exam. Oh wait, let me adjust the. There. And I'm unmuted. Okay, good. And I'm recording. Okay. So yeah, so we're gonna talk about. By the way, Marty counts. At 13 over 15. Okay, so right, so we're going to talk about this like NP completeness problem that we have, and we're gonna also have some time to like review whatever you want. Okay, so we'll just take it as we see fit. So let's open up the discussion. So we have a problem on bin packing. So the bin packing problem, let's see, you have two problems. You have the partition problem and the bin packing problem. So partition. So in the partition problem, you have a list. Integers, really natural numbers, and you want to find a subset S. Call this A, and then T is equal to like everything S, everything else in A, right? Such that the sum of all the elements in S is equal to the sum of all the elements not in S. I guess I could just write A not in S. Okay, so this is the partition problem. Okay, and this is NP complete. Okay, so we're given the fact that this is NP complete. And our objective is to show that bin packing is NP complete. What is bin packing? Bin packing is the following problem. Have again, I'll call it, let's say, what should I call it? What do they call it? They denote it as S1 Sn. And 0 is less than or equal to X is less than or equal to 1. And these are like fractional, which I guess that means that they're rational numbers. Okay? And we're given K. Also we have K. And the goal here is want to find a K partition of bin packing, okay? Such that, so the idea is we have K bins, and each of these objects that weighs like S of I pounds, so between 0 and 1 pound. And we have K bins that can each have a capacity of 1 pound. Okay? So we want to find subsets, let's say P1 Pk of these elements, right? So no element is in two. So what do we need? We need that no element is in 2 bins. So this is what I mean by partition. no two, like every two sets are disjoints, right? And union of these bias of every element is in at least one bin. So we put every element in at least one bin, but we obviously can't put an element in two bins, okay? Oh, it's X again. Okay. Right, so this is the bin packing problem, okay? And the sum of all the a's of I is at most one. All right. By the way, do you see how we could write this as a linear programming problem? Linear programming is going to be is it going to be an exam? I'm not too sure how much of it is going to be covered. But I mean, we see linear programming at least a little bit in class, right? So you should think about how to express bin packing as a linear programming problem. In particular, think of x of ij as a variable that item I ends up in bin j. Okay? And so that's your bonus problem for no, not again. Give me one of those days. Okay. Right. So the main goal of this problem, right, is we're going to show that bin packing is NP complete. At least this is the version of bin packing where you have two bins. Okay. So how can we show that? Any ideas? We know that this one over here is NP complete. So how do you show that this is NP complete? How do you show that something is NP complete? You have to show two things. What is the first thing you must show to show that it's NP complete?
That's checkable polynomial pack.
That it's in NP. That there exists an algorithm that verifies the solution in polynomial time. What is that solution? Right? Can we, like, given a positive instance of bin packing, can we give like a potential solution to it? Yeah, we can just describe each of these subsets, right? We can just give k different subsets of elements, and all the algorithm needs to do is verify that the sum of each subset is less than or equal to 1, and that every element is accounted for, and that no element is accounted for more than once. Okay? So that's the checker. So bin packing is certainly in NP. We've done that part. How do we show that it's NP apart? We use a reduction, right? So what do we reduce from and what do we reduce to? Any ideas? Remember, we already know that bin packing is a hard problem, right? So do we reduce from bin packing or do you reduce to bin packing?
Reduce to.
Yeah, you reduce to bin packing. Does that make sense, y'all? Probably quiet today. I mean, we're quiet all the time, but like especially quiet today. Okay, yeah. So we reduce to bin packing. Okay, we take an instance of partition and we reduce to bin packing. Now, how might we do that? Right? We want to find like an example such that okay, so if there are any like if there are two subsets of this that are like partitions that sum to the same thing, that is, there's a subset that sums to half of the total sum. Okay, right? This is equivalent to saying that this is just this plus this is the sum of all the elements. So if these two are equal, then each one must be the half, right? So what this is saying is that the sum of the a's of I, we need to find a set S, is equal to the sum 1/2 times the sum of everything. Okay? You see this? Now take this and try to find a reduction. Okay? Try to reduce from partition to bin packing. So I'll give you some time to do that. And if we're stuck, I'll give you a hint. Also start thinking about what else you want me to talk about. I can give you like a quick mini lecture on things and give you some exam tips on how to approach them. Oh wait, volume is off. Okay, any ideas how we might do this? So first of all, how do we okay. So there's a bit of a tricky thing here. Here we want the sum to be less than or equal to 1 of each bin, right? But here we want the sum of the two bins to be equal. Here we just care that they're less than or equal to 1. So how can we cast a condition that the sum must be equal to the sum is less than or equal to 1 for both for a bin? Now remember, we are working in a specific case where there are two bins. Okay? So whatever isn't in one bin is in the other bin. Okay? So in saying that the sum of the bins is less than or equal to each of the bins is less than or equal to 1, how can we recast the question about whether the sums are equal or not? What can we make the total sum equal to? Remember, the sum of the elements in one bin plus the sum of the elements in the other bin have to equal the total sum. And what happens if they're not equal? One is going to be less and one is going to be more. Right? How can we use that to ensure that they're both equal to each other? What can we make the total sum equal to?
Would it be 1?
We can make it equal to 1, yeah. But then what if the sum of one of them is equal to 1/2 and the sum of the other one is equal to like, no wait, that doesn't work. If one of them is equal to 1/3 and one of them is equal to 2/3. That satisfies the condition that both of them are less than or equal to 1, but it doesn't satisfy the condition that they are equal. So remember, we want the sum of both of these to be equal, less than or equal to 1. Okay? And we want them to be equal to each other.
0.
So hints, how about we let them both equal to 1? Right? Now what happens in that case? So what should we let the total sum be equal to in that case?
2.
2. Okay, so idea. Total sum. So remember again, okay, we're working in the specific case of k equals 2. This shows that the general problem is also like NP hard because this is a special case. The general case for a general k must be harder than the specific case for k equals 2. Because you can provide this case into this one. And so in the worst case, this must be at least as hard as this. Probably no k equals 3 or 4 might be even harder. But we're showing that the k equals 2 version is just as hard. Okay? So the idea is that the total sum is going to be equal to 2. Okay? And so we have T1 and T2. What we need the sum of both of these is less than or equal to 1. Right? But we must also have that their sum is equal to 2. So we'll say x is going to be the sum of everything in T1. And y is going to be the sum of everything in T2. Okay? So we know that the bin packing problem requires that x is less than or equal to 1 and y is less than or equal to 1. But we also have that x plus y equals to 2. Right? So what is the only case in this, like what if this inequality is not tight? That is, what if x is like 0.9 or something? Well, then that means y must be 1.1. Right? So if that's the case, then this isn't satisfied. So in order for this to be satisfied, both of these must be tight. Okay? Because of this condition is only satisfied when x equals y equals 1. So with this in mind, try to write out the reduction, okay? So how, in particular, how can you get the total sum to be equal to 2? Consider renormalizing each one of these. Okay? Okay, so what can we do here, right? We want to convert the set A into the set S. Okay, so what can we do? Any ideas? So we have an instance. We have an instance of partition, and we're going to convert it into an instance of bin packing. And so we'll say that capital A, or well, let's call it M, is the sum of all the A's of I. Right? So what should we do for each of these S of I? We'll find S of I equals 2. We want the total sum to be equal to 2, right?
So multiply everything by M over 2?
Almost. We divide everything by M over 2.
Yeah, okay.
Right? Okay. So what we do is S of I is equal to A sub I to A sub I over M. Okay? And you can confirm that the sum of these S of I what is the sum of the S of I? Well, you can pull out the 2 over M, and it's just equal to the sum of the A sub I, which is equal to M. The M and the M cancel, and you get 2. Okay? So now we need to argue that this is a correct reduction. What must we need to show? What must we show? We need to show that if there is a partition into two equally into two subsets of equal sum, then there exists a bin packing for this. Okay? So how can we show that? Well, let's say we have a partition, okay, into a set S and T. Well, what do we take for our two bins here? We take exactly those two. Okay? We know that the sum is equal to M over 2 for each of S and T, right? And so if we consider the corresponding elements of the bin packing problem, the sum will be equal to M over 2 times 2 over M, right? We're scaling each of these elements by 2 over M. So the sum of the, S of I is in, let's say T, for example. What is this equal to? Well, this is equal to 2 over M, the sum of the elements of A sub I. And what is this equal to? That's equal to M over 2. So the sum of T, the elements in T, and the sum of the elements in each of the bins, we certainly satisfy the condition that they're less than or equal to 1. In fact, they're both equal to 1. Okay? Does that make sense? Now, what about the other way around? What if there is a bin packing solution here? Well, if there is a bin packing solution to this problem, what must be the size of the bins?
1.
Yeah, they have to both be 1, right? Because the total sum is equal to 2, but x is less than or equal to 1, y is less than or equal to 1. Okay? If we plot out this graph, x is less than or equal to 1, okay? What does that look like? That's like this region over here, right? What about y is less than or equal to 1? That's this region over here. And then if we plot out the line x plus y equals 2, what do we get? Well, here's the y-intercept, here's the x-intercept, we get this. Okay? And their only point of intersection is right here. Does that make sense? Where x equals y equals 1. So if we satisfy this condition, and this condition, all of which we need, right, for the bin packing problem, then we are certain that the sum of the elements in T1 and the sum of the elements in T2 are the same. And so considering the corresponding elements in the partition problem, we have two subsets that partition the whole set and are equal in sum. Okay? And so that's the proof of the reduction. Does that make sense? All right, any questions about this? This one's about as, I'd say about as tricky as they'll get if we put any reduction questions on the exam. We wouldn't ask you, I mean, I think it's, given time constraints, it's too hard to ask too much on these kinds of problems, okay? Keep that in mind. What next? Can I move on to the next part? So now we're going to show that not only is this problem NP hard, we're going to show that it's hard to approximate within a factor more than 3 over 2. In other words, if we're given an instance of bin packing, right, we're going to show that it's like computationally difficult to find let's say the goal is not just to find whether or not there exists k bins, but the smallest number of bins that can pack everything. Okay? Does that make sense? The smallest number of bins such that you the smallest number of bins such that you can put things in those bins that I guess in a computationally efficient manner, we want to find the fewest bins as possible that pack all the elements. So that every element is at least one bin, and no bin exceeds its capacity. Does that make sense? Okay, so how might we show this? Let me erase this top over here. So what do we think? Any clues? Any ideas? We want to show unless p is not equal to np, there it is. Unless p equals np, pardon me, there does not exist an efficient 3/2 approximation algorithm. Does everyone understand what I mean when I say 3/2 approximation algorithm? Let's say the optimum bin is there's 2 bins in the optimum case. There's no algorithm that efficiently gives. Well, let's actually call it a less than 3/2. Let's say a 3/2 minus epsilon approximation algorithm. Okay, so for some epsilon greater than 0. This is not ruling out the existence of a 3/2 approximation algorithm. This is just ruling out the existence of like a 1.4999 approximation algorithm. Okay, so you can't do better than 3/2 unless p is equal to np. Okay, so unless p is not equal to np, there exists an efficient algorithm that there does not exist an efficient 3/2 minus epsilon approximation algorithm for bin packing. That is, assume that you can pack everything in k bins. You can't find an efficient algorithm that packs things in 3/2 minus epsilon times k. Okay? In other words, like less than 3/2. Okay. How will we show this? Well, we'll show the following. Okay? This basically means that what we're going to show, okay, is that if there exists an efficient algorithm, then p is equal to np. How can we show that p is equal to np? What is one thing we can do to show that p is equal to np? What does it mean for p to be equal to np? That means every problem in NP is efficiently solvable. In particular, the hardest problems in NP are efficiently solvable. Okay, we're considering the bin packing problem, and we've shown that it is an NP complete problem. How do we then show, right, that it's in P? Well, we find an algorithm for it, right? If we find an algorithm for bin packing in the k equals 2 case, right, then we have shown that p is equal to np. Because we've shown that k equals 2 cases is NP hard, right? Does that make sense? Okay, so proof. Any ideas? Okay, let's say the optimum bin size is 2. Okay? Then this approximation algorithm must find what? What does it have to find? It must find a solution with using at most how many bins? So suppose optimum number of bins is 2. Okay, in any bin packing instance, this approximation algorithm has to find a solution with how many bins?
When it all satisfies one with two.
Yeah, so the approximation algorithm must find solution with at most 3/2 minus epsilon times 2 is equal to 3 minus 2 epsilon bins. But bins are discrete objects. You can't have fractional bins, right? You can have bins with a fractional amount of max capacity, but every bin exists as its own discrete object, right? So if we're saying that it has to be at most 3 minus 2 epsilon bins, and epsilon is greater than 0, so we're saying we use less than or equal, we're saying we use less than 3 bins. What is the highest option the number of bins could be? 2, okay? So we must find a solution. Exactly. And how do we know we can't use 1 bin? Because the optimum is 2. Okay. By the way, the bin packing problem for k equals 1 is easy. Right? You just check the sum is less than or equal to 1. Okay. It's a bit harder for the 2 case. So what do we have here? Well, we assume that this algorithm exists, right? This 3 minus epsilon approximation algorithm. And now we have an algorithm that in the case where the optimum is 2, right? We have an algorithm to find those 2 bins. Yes? Because that's the only possible value for 3 minus 2 epsilon for a number of bins that's less than 3 minus 2 epsilon. So what does this mean? We have an efficient algorithm for the k equals 2 bin packing problem, which implies that.
But then also when I apply to like partition is also.
Yeah, exactly. So we have an efficient algorithm for partition. We reduce any instance of partition to the k equals 2 instance of bin packing. I mean, we don't even have to think about partition. We've already shown that bin packing is NP complete. But to be a bit more concrete, what we've shown here is that we can take any instance of partition and encode it in a corresponding instance of bin packing, specifically bin packing where there's 2 bins. And under the assumption that there exists a 3/2 minus epsilon approximation algorithm for bin packing, we've then further shown the existence of an algorithm that finds exactly those 2 bins. Therefore, we've shown an algorithm for partition. We reduce partition to bin packing, and then we use this supposed algorithm to find those 2 bins, thus solving partition and proving that P is equal to NP. Okay? So under the assumption that this algorithm exists, then P is equal to NP. So unless it's the case that P is equal to NP, this algorithm cannot exist. Okay? That's the hardness of approximation. And if you ever decide to take like the graduate course on approximability, if you're interested in that kind of stuff, you will do things like this. Okay, so we've shown approximation results, like there exist algorithms. In previous classes, we've shown that there exist algorithms that get to within a factor of say 2. Here we've shown that under reasonable computational assumptions, there does not exist an efficient approximation algorithm. So that's a pretty cool statement, I think. Okay. Any questions? All right. So what we do next is up to y'all. What's the time? It's like 40, 41. Okay. I mean, since we started a little late, I can go a bit late as well. So let's say we have 15 minutes. What do you want to talk about? That I can talk about in 15 minutes. Is there something on the exam that you feel uncertain about and you want me to go over?
Let me check this on the exam.
Sure. try to get to a consensus about things and then go from there. Any ideas?
I guess. I was wondering over like the halting problem again.
Yeah, is the halting problem going to be an exam?
Is that so? Like I'm not sure what he's gonna ask about. It would just be like to explain it.
Yeah, okay. I'll go over the halting problem. Does that sound good for everyone? Okay. By the way, before I forget, right? So we're getting dangerously close to the number of Smarties being the maximum amount. So just to be safe, fill out this form. tinyurl.com / Smarties. I think there are 4 people discussing today, and I remember all their names. So if you fill out this form, I'll know you were here, and you all have until all this, right? So this is if we reach 15 Smarties on Friday, I will Venmo each one of you all the unit cost of an Oreo, right? So like if you want like 10 cents or something, you can fill out this form. But yeah, okay. So right, so what is the halting problem? The halting problem is very interesting because it's the first example of a problem we've seen that is not only inefficient to compute, but it's impossible to compute. Okay. How do you cover the halting problem again? Can you do diagonalization? Is that the word diagonalization sound familiar to you all? Or do you just like argue that are you just given that it's impossible to compute?
So like the way like we went over in lecture on Monday was like just using like not like just using like the abstract idea of like a Turing machine. Like like if this that's it, if this that's the language.
Yeah. But how do you show that it was incomputable, or are you just given that?
We're given if you're on it says halting problem is undecidable.
Undecidable?
Yeah.
Okay, I mean there's not much to say beyond that. So the halting problem is, if y'all are really interested, I can give you a quick proof that it's uncomputable, but it might break your brains. So I don't know if I want to do that. So the halting problem, you're given a program P and an input X, and the question is, does halt or does P halt on input X? Okay, and some smart people in the 1920s showed that this is impossible to solve. Why intuitively is it impossible to solve? How could you know that P halts on input X? Well, you'd have to simulate it. For a general machine P, it might be very difficult to understand and just check if there's a loop or not, right? So you'd have to simulate it on input X. But in the case that it does loop forever, your program never finishes running. Okay, does that make sense? So I guess because of that, it seems extremely difficult, if not impossible, to construct a machine that solves the halting problem, right? So as for the why this is important, well, you can show that other programs are undecidable because of this. So consider the following print problem. So it takes in a program, and the question is, does he print Hukum, for example, on input X? So given a program P, and when I give it an input X, does P ever print the word like the phrase hook'em when executing on input X? Okay. This is undecidable. Why is this undecidable? Do you want me to show you why? So here is the following. So let's say this was decidable, that there's a program that terminates and outputs this, like whether or not this happens. Okay? So consider the following program Q. Following program is going to be. Oh wait a minute. Okay, it's been a while since I've done this. So okay, P print hook'em on input X, and the print is going to be akin to the halt. Oh yeah, here. Okay. Yeah, here. So run P of X. Print. Okay, so what if P does not halt? Does Q ever print hook'em? Oh yeah, by the way, we're gonna do no print statements. We're gonna assume that P does not print. If P ever prints, we'll stop it in its tracks. Okay, we'll just not output that to the console. So run P of X. So P of X is an infinite loop, right? It never prints hook'em. But if P of X finishes executing at some point, Q of X does print hook'em, right? So here is the following solution to halting problem. So to construct halt P of X, what I'm going to do is I'm going to construct Q of X and then just output I guess the input should be the tuple P comma X. Okay, so does Q halt on input the program P comma the input X, right? Well, if it prints, then P halts. If it doesn't print, then P doesn't halt. So, assuming that this program print is decidable, we have decided the halting problem for any arbitrary program. So, by the contrapositive, it must be the case that print is undecidable. Because if it was decidable, then the halting problem would be decidable. But this is our core assumption. And this is in some sense very similar to proving that something is NP-hard, right? The halt is the equivalent of our existing NP-hard problem that someone did the work and showed was undecidable, using some extremely clever and mind-bending argument that I'm not going to get into. But to show that print is undecidable, we need only show that the halting problem reduces to it in some clever way. Okay. So therefore, we've shown that's why it's significant that the halting problems are undecidable, because you can prove that other problems are undecidable. Okay. And that's probably all I'm going to say on this. Any questions? Is this a drill?
Not sure.
Is a test of the emergency
Yeah, it
warning.
wasn't.
Oh yeah, right. This happens then.
Yeah.
First one, everyone.
Yeah.
First-
If this had been an actual emergency, additional instructions would follow. This is only a test.
Okay. Thank you. Okay, so yeah, any questions?
Okay, so it's okay. So it's used to kind of show other things that are undecidable.
Yeah.
I think that's the proof you gave in class, right?
Sorry?
I think that's a proof, like similar proof you gave in class.
Yeah, yeah. This is a canonical example. Okay, so if you want a glimpse into the mind-bendingness of the halting problem, basically what happens is they can construct another program that is like, so the big idea in diagonalization, right, which is the argument for all of these things, is that programs themselves are inputs. Programs can be encoded as strings. So what we do is that we construct a new program. It's canonically called the Turing program, named after the genius who thought of it, is the idea is you take an input as your input a program, okay? And if the program halts on itself as an input, then the Turing program will loop forever. And if the program does not halt on itself, which, by the way, both of these things are decided by the halting problem. If you had a halt as a sub-function of Turing. So if the program P halts on input P, then Turing on P loops forever. And if the program on P on P does not halt, then Turing of P will halt. So the idea is to then consider Turing of Turing. Well, if Turing of Turing halts, then Turing of Turing loops forever. So it can't halt. But if Turing of Turing loops forever, then it halts. So there's a contradiction there. And so you see, if I try to explain, like when I first found this out, like I like just couldn't do anything else the rest of the day. I was just like, what is going on here? Right? So it is very confusing, but it is a good window into the weirdness of computer science and a bunch of the stuff that follows beyond this course. If you're at all interested in theory, I'd love to talk to you about it. Yeah, other than that, any questions? I don't think I have time to do anything else. Of course. Okay, so in that case, I'd like to wish you all, I'll let you all go early. I wish you all the best of luck on the exam and like everything else that follows. And thanks for being a great tech. So yeah, I'll see you all around.